Hi everyone. So what I plan to do is to use the extended handout as a basis for my discussion. The extended handout can be found on Moodle, and I'll have this up on the screen. I'll talk through it and elaborate, and hopefully this will sort of help you understand, especially some of the more difficult points on the handout. And the handout as a whole really captures the essence of this topic. So, together with the readings and any questions you might want to send my way, this will provide you with a good grounding in the topic. So, the topic, as I said, for this week will be decision theory. And I'll send an email out shortly concerning next week's topic, and I'll do a similar recording regarding that topic. So, decision theory, I think, probably a good choice on your part to cover this topic, in that it's really an interesting one, and it's one that really shows the kind of one of the virtues of formal epistemology. So in particular in formal epistemology, especially on the Orthodox Bayesian model, we are trying to represent people's degrees of belief in terms of probabilities. And one virtue of this is that it allows us to think a bit more precisely, not only about what beliefs are rational, what degrees of belief are rational, but also about what decisions are rational. So, as one might expect, one's state of belief, one's degrees of belief, might make a difference to what it's rational for one to do. So, a simple example might be that if you think it's very likely to rain, it would seem to make rational sense to take an umbrella with you when you go out, even though it might be mildly inconvenient to do this. If you think it's very unlikely to rain, then it might not be rational to take an umbrella with you. So let's start with this week. How do these rational degrees of belief, degrees of belief that might be justified, more or less, feed through into decision making? And essentially, there are two rival ways of thinking about this connection. So, two rival decision theories. The sort of classic and orthodox one is known as expected utility theory, and this is quite widely used or discussed in economics. Some of you might be familiar with it already. There's a sort of heterodox model of decision theory that has gained quite a lot of popularity among philosophers, and in some of the disciplines like computer science, but isn't quite yet, at least, as mainstream as expected utility theory. And this rival approach is known as causal decision theory, or sometimes causally expected utility theory. And so what we're going to do is introduce both of these approaches and examine basically their advantages and disadvantages, which we reckon to be the best. So we'll start with the orthodox decision theory, the evidential decision theory. Now, in order to really get to grips with it, we need to introduce some formalism. So what we want to do is we want to think about the sort of actions available to an agent. So an agent's trying to decide how to act. That's why it's a decision theory. And we might suppose that the outcomes of the action, and I guess this is what makes decision theory interesting, the outcomes of an action might not be perfectly certain, right? So imagine, for instance, the government trying to decide how to act in the face of the coronavirus epidemic. The range of actions they have available to them have uncertain outcomes. They might be able to assign probabilities to those outcomes, but they've got to make a decision on the basis of those probabilities rather than perfect certainty. So we might suppose that an action that an agent has available to them, we'll call this action A, has a number of possible outcomes. We'll denote these O1 through ON as on the handout here. Now, the outcomes are things that the agent assigns values or utilities to. Obviously, well, hopefully the government, if we consider the government to be the agent, then hopefully, for instance, their utility for an outcome involving a low death rate from the virus and maybe limited damage to the economy, hopefully their utility for that would be high. In the case of the individual agents, in the simpler umbrella scenario, presumably their utility for not getting wet is high. So anyway, the utilities attached to these various outcomes can be denoted with this sort of function, this utility function that I'm denoting with the U. So U of O1 is the utility or the value that the agent assigns to outcome 1. U of ON in general is the utility that the agent assigns to or derives from outcome ON. Now, the next point is that the agent has these probabilities, right? So they don't have certainty about the outcomes, but probabilities of the action will lead to these outcomes. And we think about those in terms of their conditional credences or conditional subjective probabilities that the various outcomes will occur given that the agent performs action A. So these are denoted just using a credence function, which we're supposing is a probability function. The probability of outcome 1 conditional upon A is something she's interested in, so the probability that she'll get wet, or stay dry rather, if she doesn't take her umbrella, is the sort of thing she might be interested in. Now, okay, so we've got the outcomes, the possible outcomes of the action A. We've got the utilities associated with those outcomes, and the probabilities that the agent assigns to those outcomes conditional upon her performing action A. So now we can calculate the expected utility that the agent associates with the action A. And what this involves is simply taking the utility of each possible outcome and multiplying it by the probability that that outcome occurs conditional upon her performing that action A. So we multiply the utility of the outcome by the probability or her credence that the outcome will occur given that she performs action A. And we do this for each outcome, and then we sum the results. And the sum furnishes the expected utility that the agent assigns to A. So essentially, what we're doing is we're taking the utility of the various outcomes, we're weighting them by their probabilities, and the result is the expected utility of the action. So we'll give a couple of illustrations of this calculation later on, and hopefully this will make it a bit more concrete and maybe a bit more intuitive. So first, that the sort of general abstract statement of what expected utility theory says is that when an agent is forced to choose between a set of mutually exclusive actions, like taking her umbrella or not taking her umbrella, then she ought to perform that one which has the highest expected utility. And just to be clear, expected utility theory on the Orthodox version understands expected utility in terms of the formula given here on the handout, whereas causal decision theory is going to use a slightly different formula. Okay, so let's illustrate this. And our first illustration is this example, which I'm calling medication. So the example is as follows. Suppose that Alice, our agent, has an illness which isn't serious, but it's unpleasant. Now, there's one known medication that can be used to treat this illness. And Alice is deciding between two mutually exclusive and jointly exhaustive actions, so there are no other actions available to her besides these two, and she can't perform both of the actions. So action A is to take the medication. Action B is to not take the medication. Now, we'll suppose that some people who take this medication suffer a fairly serious side effect. And so this can give us a sort of rich way of thinking about the outcomes. So there are sort of four possibilities when it comes to the outcomes that Alice is interested in. So outcome one is her continuing to suffer the illness and also suffering the side effect. The second one is her continuing to suffer the illness but having no side effect. The third one is her being cured of the illness but suffering the side effect. And the fourth one is her being cured of the illness and not suffering the side effect. So presumably that's the best option. Now, we'll just sort of stipulate some utilities that we'll suppose that Alice associates with these four possible outcomes. So we'll suppose that the utility that she associates with continued illness and side effect, which is presumably the worst, is a utility of -10. The second one was continued illness but no side effect. We'll suppose that has a utility of -4. The third one was being cured of illness but suffering the side effect. And remember, the side effect's serious, so maybe this is worse than having the illness but not suffering the side effect. So her utility of being cured but having the side effect, we'll suppose, is -6. And we'll stipulate that her utility for being cured of the illness and suffering no side effect is in other words, +5. These are more or less just sort of arbitrary stipulations. We could have stipulated it another way, but this just gives a bit more concreteness. I mean, of course, there's a sort of question about exactly how we measure utilities and whether we can measure utilities, which is a sort of difficulty or a challenge, at least for all forms of decision theory. One approach is to try to get a handle on this in terms of agents' preferences. So, for instance, if someone prefers ice cream to peas, then one can suppose that the utility that they associate with eating ice cream is greater than the utility that they associate with eating peas. And if someone's indifferent between ice cream and trifle, one can suppose that those utilities are the same. Now, this sort of gives you a ranking, sort of a preference ranking or a utility ranking. And then the big challenge is to try to see whether we can assign cardinal values, that is numerical values to those utilities, and not merely a ranking. So there are some sort of clever attempts to do this that we won't go into for the purposes of this topic. It takes us a bit too far afield, and we'll just suppose that this is in fact possible. Right. So the final part of our example is to stipulate or specify the conditional probabilities that Alice assigns. In other words, her conditional subjective probabilities or conditional credences. So let's suppose that, remember, A is the action of taking the medication, B is the action of not taking the medication. Suppose that the probability of the unfortunate case in which she continues to be ill and suffers a side effect as well, so the medication can produce a side effect, and we're also supposing that it's not completely reliable in preventing the disease or curing the disease. So the probability that she'll continue to have the disease and unfortunately suffer the side effect, we'll suppose, is 0.05. The probability that she will continue to have the disease but not have the side effect, we'll suppose, is that is given that she takes the medication, is 0.2. The probability that she'll be cured of the disease and suffer the side effect if she takes the medication is 0.1, and the probability that she'll both be cured and not suffer the side effects of the best outcome, we'll suppose, is 0.65. Now, when it comes to action B, the possible action of not taking the medication, we can suppose that, we'll just, for simplicity, suppose that the probability of her being cured is 0 if she doesn't take the medication. So that means the probability of O1, the outcome in which she's cured and suffers a side effect, and the probability of O3, outcome O3, in which she's cured but doesn't suffer the side effect, they're both 0, conditional upon her not taking the medication. Now, we can suppose that the probability that she isn't cured but suffers this. Oh, sorry, I've got this the wrong way around. So what I should have said is we should suppose that if she doesn't take the medication, the probability of her suffering the side effect is 0, right? So actually, in these probabilities, I've assumed there's some probability of her getting better all by herself without taking the medication. So actually, what the first probability says is that the probability of her her not being cured and suffering the side effect is 0, and the third one says that the probability of her being cured and suffering the side effect is 0, and that's just because the probability of her suffering the side effect is 0, given that she doesn't take the medication. So the second one says that the probability of her not suffering the side effect and not being cured is 0.9, given that she takes the medication. Sorry, I'm just I've kind of confused myself with this. I'm not sure I've got the probabilities the right way round. Let me just okay, so illness and side effects should be 0. That's right. So the first one's right. Yeah, I've got these the wrong way round on here, which is what was confusing me. There's a typo. So O1 is illness and side effect. So that should be 0 because there's 0 probability she gets a side effect if she doesn't take the medication. O4 is no illness and no side effect. So that's okay as being positive. O3 is no illness and side effect, so yeah, that should also be 0 because she doesn't take the medication in scenario B. Right, yeah. So I haven't got this wrongly around at all. I'm just getting myself confused for no good reason. O2 was a scenario in which she continues to have the illness but doesn't have the side effect, right? So of course we should suppose that to be quite high, given that she doesn't take the medication. So the probability that she'll continue to have the illness and not suffer the side effect is quite high, given option B, that she doesn't take the medication, so 0.9. Whereas the probability that she spontaneously recovers but doesn't have the side effect is comparatively low, given that she doesn't take the medication at 0.1. So sorry about the confusion there. I just confused myself. What's stated on the handout is exactly right. Okay, so we've gone through all of these numbers. And finally, we can calculate the expected utilities associated with option A, taking the medication, and option B, not taking the medication. And recall that what we do is, for instance, in calculating the expected utility of option A, is take the utilities of each of the possible outcomes associated with A and multiply these by the probability that the agent assigns to that outcome being the one that materializes conditional upon A, and then sum up the results. So in the example in hand, we have 4 possible outcomes, O1 through O4. What the agent wants to do, for instance, is take the utility that she associates with O1, multiply it by the probability that O1 comes to pass, conditional upon A, take the utility associated with O2, multiply it by the probability that she gives for O2, conditional upon her performing action A, and so on for 3 and 4, and then add up the results, and that gives the expected utility associated with the action A. So this is the rest of the calculation is just simply a matter of calculating from the numbers that we've given above. So we just plug in the numbers that we've given above for each of these terms, and then we just perform some basic maths. We get the result that the agent's expected utility associated with taking the medication is 1.89. Like very exactly analogously for option B, not taking the medication, obviously there we're interested in the probability of the outcomes conditional upon not taking the medication, conditional action B rather than A. So we just perform the calculation given the numbers that we've been given above, and we arrive at an expected utility associated with B, not taking the medication, of negative 3.55. So obviously positive 1.89 is greater than negative 3.55. So at least on the assumption that the agent's probabilities and utilities are as we described, expected utility in its orthodox form tells us that Alice shouldn't take the medication. Okay, so that just provides an illustration of the standard workings of the theory. Hopefully it seems reasonably intuitive. It's most people, at least initially, find it reasonably attractive. As I say, it's kind of the orthodox theory. So it's the orthodox theory in economics, and it's certainly very popular in philosophy. Now, what we want to do now is to introduce the rival theory of causally expected utility theory, or sometimes called causal decision theory, and compare and contrast the two theories. But in order to do so, it's actually going to be helpful to take a little bit of a detour to help us understand causal decision theory more when we come to set it out formally. And the detour firstly involves thinking about this notion of states of the world. So often when we're doing decision theory, it's helpful to think kind of quasi-deterministically. So the idea is that we suppose that which outcome occurs in a decision scenario depends upon, firstly, what action the agent performs, but also the state of the world, right? So the agent isn't perfectly knowledgeable about the state of the world, hence she's uncertain about what consequences her action will produce. So, for instance, the government, think about the government making the decision about how to respond to COVID-19. Well, the government faces a lot of uncertainty about the state of the world. They face uncertainty about how many people actually have the virus at the moment. They have uncertainty about exactly who is tends to be infected by the virus. They have uncertainty about whether there'll be a vaccine developed or when it will be developed. They have uncertainty about these sorts of, how people respond to the virus, what sociologically, whether people will actually self-isolate as they're advised to, and so on. So there's a lot of uncertainty that the government faces about the state of the world, about people's intentions, about the prospects for treatment and cures or vaccines, and this is what makes, or at least part of what makes them uncertain what outcomes in terms of things like death rates and infection rates and economic damage will result from the various actions they can take in response to the virus. So, sort of one way of thinking, and it's just simple to sort of think about the world as kind of being underlying deterministic. We don't actually really need this, but it's a sort of useful heuristic. I've applied it to Alice's case in making her decision about whether to take the medication on the handout. So, for instance, we might suppose that whether or not Alice is cured and whether or not she suffers a side effect depend not only on her action, but also facts about her genetics and other aspects of her physiology. Now, these are the facts that are part of what we're calling the state of the world. And we might suppose there's kind of a partition of states of the world, or types of state of the world, W1 through W4. And these are the ones that are going to make the relevant difference to what results from Alice's action. So, for instance, we might suppose that her taking the medication deterministically produces outcome O1, that is her being not being cured and her suffering the side effect if the state of the world is W1, whereas her action produces outcome O2 if the state of the world is W2. It produces O3 if the state of the world is W3, and O4 if the state of the world is W4. So we're thinking quasi-deterministically. So in other words, for each outcome and corresponding state of the world, Wi, the corresponding outcome is Oi, the probability of, and this I guess should be thought of in terms of an objective probability or chance, the chance of outcome Oi, conditional upon her performing action A, and the state of the world being Wi is 1. So that's just to say that actions combine with states of the world to bring about outcomes with certainty. And so the agent's uncertainty is just to be thought of in terms of her uncertainty about the state of the world. Now, the flip side of that is that given that the outcomes are mutually exclusive and the states of the world are mutually exclusive, if the state of the world is not Wi, then the agent's action is going to combine with it in such a way as to deterministically not produce the corresponding outcome Oi. So the probability of Oi conditional upon, and this is an objective probability again, the probability of Oi conditional upon A and not Wi is 0. So the upshot is, this is a little bit complex. Well, it's not that complex, but it's sort of feels a little bit tangential at this stage, but hopefully the relevance will be seen later on. Is that basically it can be proven relatively simply, and I've done this in the appendix, which I won't go through. You can read it through yourself. It's straightforward. That from what we've said, it follows that basically the agent's uncertainty about what outcome will happen conditional upon her action can be reduced to her, or is the same as her uncertainty about what the state of the world is. So hopefully that's fairly intuitive in light of what's gone previously. Now, if we assume that the state of the world is independent of the agent's action, then the probability that she assigns to the state of the world being Wi, conditional upon her action, should be the same as, or is the same as, the probability of Wi. That's just what it means to be probabilistically independent. So the agent's action is independent in the sense that her performing the action neither raises nor lowers the probability of the state of the world being Wi. So, for instance, in the Alice case, her taking the medication, we're supposing, doesn't influence her genetics and her pre-existing physiology. All right, so the next step is that it follows from equalities 3 and 4 that the agent's conditional probability for the outcome OI conditional upon her action A is just her probability that the state of the world is of the corresponding one Wi, namely the one that combines with A to produce outcome OI. No, okay, so the upshot of all this is that where this is true, where the states of the world bring about the outcomes in combination with actions, where the state of the world is independent of the agent's actions, we can reduce or I suppose simplify somewhat, our expected utility formula, so that it just says that the probability or the expected utility that the agent associates with action A is the weighted sum of the utilities of the various possible outcomes of action A, where they're weighted by the probability that the agent assigns to the corresponding state of the world obtaining. All right, so that's all fairly abstract, but some of this will become hopefully become a bit more intuitive and a bit more applied later on. Okay, right, now let's next shift topics slightly, but we'll see how these topics interact, and consider what's known as the dominance principle, which seems like a condition on rational decision. Now, the obvious question is, how does the dominance principle relate to the principle of maximizing expected utility, which is what expected utility theory says? And we'll see exactly how they relate as we go on. But the dominance principle on its own seems rather plausible. So, suppose, to see what the dominance principle says, let's suppose that the states of the world are independent of the agent's action. Now, so this is something that was presumed in equality 4. So the state of the world is independent of whether the agent performs action A. It might also, as equality 6 says, be independent of whether she performs action B. And in general, it might be that the state of the world is independent of any action that the agent could perform. Now, the dominance principle says that if A and B are mutually exclusive and jointly exhaustive actions, then if in each state of the world, so regardless of what the state of the world is, the outcome produced by action A is at least as good as, or in other words, has at least as much utility as, the outcome produced by the action B. And if in at least one state of the world, the outcome produced by A is superior to, in other words, produces more utility than the outcome produced by B, then A dominates B, right? So dominance is A dominates B if in at least one state of the world A produces a better outcome than B, and if in no states of the world B produces a better outcome than A. So the dominance principle says that if A dominates B in this way, then the agent should perform action A, and that seems pretty plausible. Right, yeah. So an example of this is a straightforward example of a free bet. This example 2. So suppose you're offered a free bet that pays £100 if a fair coin lands heads and 0 otherwise. So there's no charge for taking this bet. You can take it for free. A could be the action of accepting this free bet. B, the action of declining the free bet. Then, I mean, it's fairly easy to see that, it's fairly intuitive that one should just take the bet, right? So, it produces a better outcome in one state of the world, namely where the coin lands heads, and no worse an outcome in the state of the world where the coin lands tails, because if the coin lands tails, you're just where you were. You've spent zero on the bet, you've received zero payoff. But in the good state of the world, you've paid zero for the bet and received £100 in payoff. So it seems obvious you should take the bet, and that's what the dominance principle says. So, I mean, we could tabulate this. So, it's fairly obvious. So, action A is taking the bet, accepting the bet for free. Action B is declining the bet even though it's free. So those that given the options given at the top of the table, and then on the left of the table, the first column, the states of the world, heads and not heads. So those are the two states of the world. And if the agents accepted the bet, performed action A, and heads arises, she gets £100. Actually, I'm kind of supposing that, just for simplicity, that each pound corresponds to a unit of utility. That's a rather simplistic assumption. So I'm supposing that if the agent gets £1, then she has like 1 unit of utility. If she gets £2, she has 2 units. If she has £0, she has 0 units. If she has £100, then that gives her 100 units. That's simplifying for various reasons, one of which is that it supposes that the marginal utility associated with money for the agent is constant. So actually, normally we probably suppose that that utility declines in money. So your first £10,000 brings you a lot more utility than your second £10,000, which brings you a lot more utility than your thousandth £10,000. So we could suppose that the bets a way of avoiding this assumption would be to expect that somehow the bet is conducted in terms of units of utility rather than pounds. So if heads happens, then you get enough money to give you 100 units of utility, even if that might not be £100. But anyway, we don't really need to worry about that complication for present purposes. Okay, so here the dominance principle seems very plausible, and actually the expected utility calculation is also going to indicate that you should perform heads. You can calculate that for yourself. It's very simple. But there are some circumstances in which the dominance principle isn't plausible, and specifically the dominance principle isn't plausible when the state of the world isn't independent of one's action. So there's hopefully an intuitive example of this is example 3 on the handout of the exam. So this example may be a bit close to home for some of you, but I'm going to suppose you are offered a free bet that pays $50,000, £50,000, whatever, if you get a first in your exams and 0 if you don't. Now, as before, we can let action A be the act of accepting this free bet and action B the act of declining this free bet. Now, suppose that we're supposing again just the simple equation between utility and money. And another assumption I'll make is that getting a first in your exams on its own, without the extra payoff, would bring you the same utility as $50,000 on its own. I don't need to make that assumption, but it's just a straightforward one to make. So uh, getting getting a first would bring you 50,000 units of utility, or 50 units of utility. Getting $50,000 would give you 50,000 units of utility as well. Or I'll simplify by supposing it's 50 again. Okay, good. So then what matters is the relative utilities, not the absolute utilities. So it's fine to assume both bring 50 units of utility, or 50,000. It makes no difference, because all we're interested in is the relative utilities. So basically, this sort of decision problem is represented in table 2. And so again, at the top of the table are the actions available to the agent, so she can accept the free bet or she can decline the free bet. And on the left are the states of the world, so she gets a first, she doesn't get a first. So if she gets a first, having declined the bet, then she gets 50 units of utility, which is just the intrinsic value to her of getting a first. If she accepts the bet, and also gets a first, then she gets twice as much utility. She gets 100 units of utility rather than 50. If she doesn't get a first, then no matter whether she accepts the bet or not, she gets 0 units of utility, because firstly, she doesn't get the utility associated with first, and secondly, because she's because she doesn't get a first, no matter whether she accepted the bet or not, she doesn't get the payoff of the bet. So we can see from this table that accepting the bet, that is action A, dominates action B, and that's because regardless of what the state of the world is, it brings at least as much utility as action B, and in one state of the world it brings more utility. So specifically, in the state of the world in which she gets a first, action A, accepting the bet, brings more utility than action B, 100 versus 50. And in the other state of the world in which she doesn't get a first, A results in no less utility than B does, because they're both zeros. So this implies that A dominates B. So the dominance principle would seem to suggest that the agent ought to accept the free bet. Now, there is a problem for the dominance principle, however, if we let the decision made by the agent have an influence on the state of the world. So we could give a sort of fairly natural story about how this might happen. So suppose when you're considering whether to accept this free bet, you know that the extra pressure of the potential $50,000 is going to make you more nervous about your exams than you'd otherwise be, because now there's more riding on it. So not only is it the intrinsic value of a first, but it's also this additional 50 grand that you stand to potentially win. So you can see how that might make you more nervous. It might increase the pressure. And suppose that you know that nerves tend to make you perform less well in exams, certainly too many nerves, then it might be that, or then it will be that your credences concerning the state of the world, i.e. whether you get a first or not, aren't independent of whether or not you accept the free bet. Specifically, declining the bet makes it more likely that you'll get a first than does accepting the bet. And so in this scenario, we'll see that although accepting the bet dominates declining the bet, it's a lot less plausible that what you should do is accept the bet. So specifically, we might suppose that the probability or your credence that you'll get a first if you accept the bet is 0.2, whereas your credence that you'll get a first if you decline the bet is 0.9. So that's just it's just equality 7 and 8 on the handout. Now, we can apply a theorem of the probability calculus, conditional complementation. So we can get to derive the probability of not getting a first conditional upon accepting the bet and not getting a first conditional upon declining the bet. So the probability of not getting a first conditional upon accepting is 0.8, just because the probability of getting first conditional upon accepting is 0.2. And the probability of not getting a first conditional upon declining is 0.1, just because the probability of getting a first conditional upon declining is 0.9. Okay, so then we can just do our expected utility calculation using the formula that we originally introduced. And the expected utility for such an agent of action A is the utility associated with performing A and getting a first, namely 100 units of utility, multiplied by the probability that she gets a first if she performs that action A of accepting the bet, which we've given as 0.2. So that's the first term. And then to that we add the utility of not getting a first, which is 0, multiplied by the probability of not getting a first, conditional upon performing action A, which is 0.8. So that second term obviously becomes 0. The first term is 20. So overall, the expected utility of accepting the free bet in this scenario is 20. On the other hand, when we calculate the expected utility of action B, what we do is we take the utility associated with getting a first if she performs action B, namely declining the bet, which is 50 units of utility, multiply that the probability that she'll get a first if she performs action B, which is 0.9, higher than if she performs action A. So 0.9 times 50, which is 0.45. Sorry, it's not 0.45, it's 45. And we add that to the utility that she'd get if she doesn't get a first, namely 0, by the probability that she won't get a first if she performs action B, which is 0.1. So this cancels out to 0. And so we get an overall utility of expected utility of 45. That's a typo where it says 0.45. It should say 45. Okay, so what we find is that actually the expected utility of declining the free bet in this case is higher at 45 than the expected utility of accepting the free bet, which is 20. So expected utility theory recommends accepting the bet, and so in this case it conflicts with the dominance principle. And so basically what's going on is that the accepting the bet makes you so nervous about your exam that it just reduces the chance very strongly that you'll get the first and therefore derive the intrinsic value of that and get the payout. And it's so strong that it's actually better not to accept the bet in the first place, according to expected utility theory. So it contradicts the dominance principle. We've seen that the dominance principle implies that you should accept the free bet in this case. Um, Moreover, I think intuitively it just seems that the implication of expected utility theory here is right, and the implication of the dominance principle is just wrong. So it's implausible that the dominance principle applies when the outcome's not independent of the state of the world. In this case, the outcome being the whether you the amount of money you win. Oh, sorry, the amount of utility you derive, and the state of the world being whether you get a first or not. Your action influences of accepting the bet versus not accepting the bet affects the probability of you getting a first or not, and so that explains why the dominance principle isn't plausible in this case. Okay. Okay. Now, before we finally introduce causal expected utility theory, which is going to play on this issue of an action's influencing the state of the world, we need another distinction which will allow us to compare causal decision theory to evidential decision theory, or standard expected utility theory, in other words. Now, in the case we've just described, so we've seen that the recommendation of orthodox expected utility theory appears to be the right one. The recommendation of the dominance principle appears to be the wrong one. Now, sort of what's happened there is we found that the reason for this was that the state of the world wasn't probabilistically independent of your action. Why wasn't it probabilistically independent? That is, why was your getting a first or not, the state of the world, not independent of whether or not you accepted the bet? Well, it seems to be something to do with causation, right? So accepting the bet causes you to be nervous, and being nervous causes you, or at least has a causal tendency, to prevent you from doing well in the exam. So the state of the world, in other words, how well you perform in the exam, is causally affected by your action to accept the free bet. Now, there are other cases in which an outcome, or a state of the world and therefore an outcome, is not probabilistically independent of your action. But that's not because your action causally affects the outcome. And in these sorts of cases, actually, it seems the dominance principle, rather than orthodox expected utility theory, that seems to be the more plausible principle in these cases. So let's illustrate again. An example will make this more concrete. So this is example 4, smoking, right? So we all know now that smoking tends to cause lung cancer. Now, there was a time, I think, back in the 60s, I think, when obviously a lot of scientific evidence was starting to point towards a causal link between smoking and lung cancer, and people get increasingly concerned about this. The tobacco companies obviously were worried about this because apparently not because they were concerned about people's health, but because they were concerned about the impact that this could have on their profits. And they tried to defend themselves against this claim that smoking causes cancer. And what they said is, or at least they speculated, that there was a gene that some people had that firstly made them more likely to smoke, and secondly made them more likely to get cancer. But it brought about these effects independently. So if you have the gene, you're more likely to smoke, and you're independently more likely to get cancer. So rather than the smoking bringing about the cancer, their speculation or their claim was that there was some gene that causes each of smoking and cancer independently. So that was the claim. It's now been discredited. But let's just suppose, for the sake of this example, that the tobacco companies had turned out to be right, so that the gene causes both smoking and cancer rather than smoking itself causing cancer. Now, if that were right, then suppose that we've got someone who likes smoking and they're deciding whether to continue smoking or not. Suppose that smoking will, because they like smoking, bring them some utility, maybe 10 units of utility. But this isn't nearly as much as of course, the disutility associated with getting cancer. Well, suppose that's minus 1,000 units of utility. Now, in this sort of hypothetical world, the relevant states of the world concern whether the agent has the gene or not, the gene that, according to the tobacco companies, produces both smoking and cancer. Now, the associated utilities are set out in Table 3. So if the agent has the gene and smokes, and I'm supposing, just for simplicity, that the gene deterministically brings about cancer, then the agent is going to get minus 990 units of utility, because she's going to get cancer, which brings her minus 1,000 units. But because she's decided to smoke, and smoke brings her 10 units of utility, this is going to a very small degree, offset some of the negative utility of the cancer. And so we're going to subtract the 10 units of utility from the 1,000 units of disutility, and the result is we get a number negative 990 for the disutility she gets if she smokes and has a gene. If she smokes and doesn't have the gene, then she doesn't get cancer. And she does get the 10 units of utility from smoking. Okay. On the other hand, if she chooses not to smoke, that is decision B, and she has the gene, then she gets a negative 1,000 units of utility because she gets cancer in virtue of the gene, and there's no offset because she doesn't get the 10 units of utility from smoking. On the other hand, if she decides not to smoke and doesn't have the gene, then she gets 0 utility. So she doesn't get the negative utility of cancer because she doesn't have the gene, but she's also decided not to smoke, so she doesn't get the positive utility of smoking. Now, interestingly, in this case, action A dominates action B. In particular, in both states of the world, action A of smoking has higher utility than action B of not smoking, because smoking offsets some of the disutility associated with cancer if the agent has a gene. And in the case where she doesn't have the gene, well, she still gets the 10 units of utility from smoking. So in this case, the dominance reasoning actually seems pretty plausible, I think. So if we set aside what we actually know, which is that smoking causes cancer, if we suppose that the tobacco company's dream had come true, and that you're either born with this gene or you don't, and whether you smoke has no effect on whether you have this gene, then it seems that if you do enjoy smoking, then you might as well smoke, because nothing you can do affects whether you have this gene. So you might as well get those 10 units of utility from smoking. Okay, now in this case, it's worth noting that the state of the world, even though the dominance reasoning looks right, in this so the dominance principle looks right, but in this case, as in the last case, the exam case where the dominance reasoning looked wrong, it's also true that the state of the world isn't probabilistically independent of the agent's decision. Specifically, the probability that the agent has the gene, given that she smokes, is greater than the probability that she has the gene, given that she doesn't smoke. And that's because the gene causes both smoking and cancer. And because it causes smoking, it means that people who smoke are more likely to be ones who have the gene. So the probability of having the gene is higher if you smoke than if you don't, not because smoking causes you to have the gene, but rather because it's an effect of having the gene. So this is just analogous to someone saying that if you have a temperature, you're more likely to have coronavirus than if you don't have a temperature. It's not because having a temperature causes coronavirus, but it's rather because having a temperature is an effect of having coronavirus. Sorry, all my examples about coronavirus these days. All right, so we could suppose that specifically equalities 11 and 12 hold. So equality 11 says the probability that the agent has the gene, given that she smokes, is 0.9. The probability that she has the gene, given that she doesn't smoke, is 0.2. Now, if we have those probabilities, then we can form an expected utility calculation given the utilities set out in table 3. So we can calculate the expected utility associated with smoking by multiplying the utility of smoking, if you have the gene, by the probability that you have the gene given that you smoke, which is 0.9. So that gives a first term of negative 891. So the utility of smoking if you have the gene is negative 990. Multiply that by 0.9, which is the probability that you have the gene if you smoke, gives a result of negative 891. On the other hand, we look at the scenario in which you smoke and don't have the gene. The utility associated with that is 10, and multiply that by the probability that you don't have the gene if you smoke, and that's 0.1, and 10 times 0.1 is just 1. So the expected utility associated with smoking is negative 890. Now we can calculate the expected utility associated with the decision not to smoke, and that's just very similar. So the utility of uh, uh, if you perform action B and have the gene is negative 1,000. Multiply that by the probability that you have the gene conditional upon not smoking, which is 0.2. That gives us a figure of negative 200. On the other hand, the utility of not having the gene and not smoking is 0, and we multiply that by the probability that you don't have the gene if you don't smoke, and that's 0.8, but obviously that cancels to 0 because you're multiplying by 0. So the overall expected utility associated with not smoking is negative 200. So, interestingly, here in this smoking example, expected utility theory, standard expected utility theory or evidential decision theory gives the verdict that you ought not to smoke. That's because the expected utility of that decision is negative 200, whereas the expected utility of the converse decision to smoke is negative 890. So obviously negative 200 is greater than negative 890. So expected utility theory mandates not smoking. But that seems like the wrong verdict, right, in the case where we're supposing that smoking doesn't cause cancer. Because it seems like because smoking doesn't cause cancer, you might as well smoke, right? So either you have the gene or you don't. There's nothing you can do that will affect whether you have the gene. And if you have the gene and smoke, then you get more utility than if you have the gene and don't smoke. And if you don't have the gene and smoke, you have more utility than if you don't have the gene and don't smoke. So there's a dominance principle in play. And here, what you do doesn't affect the state of the world. So it seems like you might as well smoke. So a lot of people find the recommendation of expected utility theory in this sort of case to be implausible. Okay. So I suppose a sort of interesting moral to take home from the smoking example versus the exam example. So in both cases, the state of the world wasn't independent of the decision. However, in the exam case, the state of the world wasn't independent of the decision because the state of the world was causally influenced by the decision. So whether you get a first is causally influenced by whether you take the free bet, because the free bet affects how nervous you are. In the smoking case, although there's no probabilistic independence of the state of the world from the decision, so although you're more likely to have the gene if you smoke, that's not because smoking causally influences whether you have the gene and therefore whether you get cancer in this scenario. But rather it's because they're kind of independent effects of a common cause. They're correlated because they have a common cause, or rather the states of the world are correlated because they have a common cause, namely having the gene. And the reason that the action is correlated with having the gene is not because the action causes whether the gene is had, but rather conversely because the gene causes the action or tends to cause people to smoke. So in cases, it seems, where causation of the state of the world by the action explains why the right. Sorry. I should say, in cases where it looks like your action actually causes the state of the world or causally influences it, it seems more plausible that you should take that into consideration than cases where your actions correlated with the state of the world, but doesn't cause the state of the world, as in the smoking case. And this is essentially what causal decision theory is saying. So causal decision theory is sort of a rival to evidential decision theory. You could view it as a heterodox version of expected utility theory, whereas evidential decision theory is the orthodox version of expected utility theory. It's one that has gained quite a lot of popularity among philosophers. Now, basically, causal decision theory is telling us not to confuse causation with correlation, right? So the claim is that expected utility theory tends to get the wrong results in some cases because it conflates causation with correlation, or because it's insensitive to the difference between causation and correlation. So the claim of causal decision theory is that we should focus not on the probabilities that various outcomes have conditional upon our actions, but rather on the tendency of our actions to bring about those outcomes. This causing or bringing about is normally understood in counterfactual terms. So some of you will have previously studied causation, maybe as part of a metaphysics class. And you'll know that one theory of causation is a counterfactual theory. So for A to cause B, what it means for A to cause B is for it to be the case that if A hadn't happened, then B wouldn't have happened. So we say, for instance, that the impact of the brick caused the window to break, and what that amounts to is the claim that if the brick hadn't hit the window, then the window wouldn't have broken. So causal decision theory is interested not in the probability of the outcome conditional upon the decision, but the probability that if you were to perform action A, then some outcome would occur. Now, as some of you will be familiar with, but not all of you, there's a sort of standard way of formulating or formalizing counterfactuals in terms of the box arrow notation given on the handout. So a box arrow OI is to be understood as the counterfactual that says that if I performed action A, then outcome OI would occur. Now, the causal decision theorist tells us we should be interested not in conditional probabilities of outcome OI given A, but rather in the probabilities that the counterfactual holds that if I were to perform A, then OI would be the result. So the causal decision theorist version of expected utility theory, this heterodox form of decision theory, tells us that we should assess what's known as the causally expected utility of action A rather than the standard expected utility of action A. We could denote this EUC of A. And the formula they give is this one on the handout. So this says that the causally expected utility of A is again a kind of weighted sum of the utilities associated with the possible outcomes of A, but rather than weighting the utilities of the possible outcomes by the probability of those outcomes conditional upon the performance of A, rather we weight them by the probability that a counterfactual holds, a counterfactual that says that if A had happened, or if I were to perform A, then outcome OI would result. We'll give an illustration of this, and we'll see how this differs from the from the evidential decision theorist's recommendation. So, causal decision theory, just to be clear, says that when an action is faced with a set, when an agent is faced with a set of mutually exclusive and jointly exhaustive possible outcomes, she should perform the one with the highest expected utility. Where expected utility, I should say, is understood in terms of this formula. So it's causally expected utility, as distinct from the evidential decision theorist's formula. Okay, so what does this imply about the smoking example? Well, note that if the agent thinks that whether she smokes or not doesn't causally influence whether or not she has the gene, then her credences will be such that the probability she assigns to the counterfactual, if I smoke, then I'll have the gene, should be equal to the probability she assigns to the conditional, if I don't smoke, then I'll have the gene. That is just a sort of fancy way of saying that the agent believes that whether or not she smokes makes no difference to whether or not she has the gene. So there's no sort of causal tendency of her smoking or her decision to smoke to influence whether or not she has the gene. Okay, right. So she might well think that the probability of her having the gene is higher conditional upon her smoking, just because the gene tends to cause smoking, but she doesn't think that the decision whether to smoke has a causal influence on the probability of whether or not she has the gene. And because she doesn't think it has a causal influence upon whether or not she has the gene, she doesn't think that it has a causal influence on whether or not she gets cancer. Like, she doesn't think a decision has that causal influence on whether she gets cancer. So, all right, so the agent we're supposing believes this tobacco company story, and in fact, just to make things clearer, we'll suppose that we're in a world in which the tobacco companies have been correct, that actually deciding whether or not you smoke doesn't influence whether or not you get cancer, because they're both explained by whether or not you have this gene. So this equality on the handout holds, so the agent thinks that the probability that she has the gene if she smokes is, or the probability she would have the gene if she would smoke, is equal to the probability that she would have the gene if she didn't smoke. And we'll let X stand for whatever this value is. So the two probabilities are equal. We'll suppose that X is whatever the probability she assigns to these two possibilities. Okay. Now, remember that we're supposing for simplicity that everyone who has the gene develops cancer, and everyone who doesn't. Then we can calculate the causally expected utility fairly straightforwardly. So X, remember, stands for the probability of the two conditionals, which are equal. And what we want to do is multiply, according to this formula for expected utility theory, we want to multiply the utility that she gets if she smokes and has the gene by the probability X that if she smokes, she has the gene. And we want to add that to the utility that she gets from smoking if she doesn't have the gene, multiplied by the probability that if she smokes, she doesn't have the gene, which is just going to be 1 minus the probability that if she smokes, she does have the gene, so 1 minus X. So we just need to do some algebra now. The first term gives a result of minus 990x, where x is this probability. And we just multiply out the brackets in the second term, so we get 10 minus 10x. So simplifying, we have just by doing the algebra, we get the result that the causally expected utility of smoking is equal to 10 minus 1000x. We do the same sort of calculation for the option of not smoking, and so we multiply the utility of not smoking if you have the gene, which is negative 1000, by this probability X, which is the probability that if you don't smoke, you have the gene. You add that to the utility of not smoking if you don't have the gene, which is 0, multiplied by the probability that you don't have the gene if you smoke, which is equal to 1 minus the probability that you do have the gene if you smoke. And again, just some basic algebra yields the result that the causally expected utility of not smoking is negative 1000. Now, note that this means that the causally expected utility of not smoking is lower than the causally expected utility of smoking, right? Because the causally expected utility of not smoking is negative 1000x, whereas the causally expected utility of smoking is 10 minus negative 1000x. And because 10 is positive, that means that that's a greater utility than the causally expected utility of B. So the causal decision theorist actually recommends that you smoke in this case, which is in accordance with the dominance reasoning, but contrary to the verdict of the evidential decision theorist. And in this case, where we're supposing it's true that smoking doesn't causally influence whether you get cancer because there's a gene that explains both, then the causal decision theorist seems to intuitively, I think, have the right verdict. Now, the Newcomb problem, which you'll have come across in your reading, is just very similar to example 4, but it's a bit more extreme. And so I guess brings the difference between causal decision theory and evidential decision theory into sharper relief. So it was actually partly in response to the Newcomb problem that causal decision theory was first developed. So the problem's as follows. It's a bit science fiction-y, a bit fanciful. So we suppose that there's a demon who is an exceptionally reliable predictor of people's choices. The demon has a huge track record of successful prediction, both of your decisions and other people's decisions. The demon has some method. Maybe they study people's brains with an MRI or something, and somehow they're an expert in brain science. And somehow the demon, sort of via this method, knows not only what you're going to decide before you've decided, but even knows what your response will be well ahead of your being confronted with the decision problem. So, in other words, effectively, the daemon looks at your brain at some initial time and then knows how you respond to any possible decision that you might be confronted with. The demon has an exceptional track record, so maybe gets only 1 in a billion predictions wrong. Now, this demon likes to play a game with people, and this the Newcomb Problem game. The decision that people make is among those that the demon is enormously successful in predicting, only gets 1 in a billion wrong. So the game is as follows. The demon places 2 boxes in front of the participant. Box 1 is transparent, so the participant can see the contents, and it contains $1,000. The participant can see this. Box 2 is opaque, so the participant can't see what's in it. But the demon tells the participant, we'll suppose the participant trusts the demon. The demon tells the participant that the box contains either $1 million or no dollars. Now, the participant is given the choice by the demon whether to open just box 2, the one that is opaque and contains either $1 million or nothing, and to keep anything that she finds in box 2, or to open both boxes and keep the contents of both boxes. Now, the demon operates as follows. If it has predicted that the participant will just choose to open box 2, the opaque one, then it has put $1 million in box 2. If it is predicted that the participant will choose to open both boxes, then it has put $0 in box 2. Now, suppose you find yourself to be a participant in one of these games. The question is, what should you do? Now, in fact, among philosophers, the Newcomb Problem splits opinion between so-called one-boxers who think that rationality requires taking just box 2, and so-called two-boxers who think that rationality requires taking both boxes. So there seem to be good arguments for both for one-boxing and for two-boxing. So the argument for one-boxing is that if you take both boxes, then the demon will have predicted this and will have put $0 in box 2, so almost certainly you'll get only $1,000. But if you took box 2 alone, then you'd almost certainly get $1 million. So you might think, well, it seems that you should one box, right? So why take both boxes if this almost guarantees you only $1,000? Where taking only box 2 would guarantee you, almost certainly guarantee you $1 million. It seems intuitive to one box. The argument for two boxing, on the other hand, is that the demon's already made its prediction and has already put either $1 million or $0 in the opaque box 2. If the demon's already put $1 million in box 2 and you two box, then you receive $1 million plus the $1,000 in box 1. Whereas if you one box, you'll receive only $1 million. So you get the sort of $1,000 kind of for free by taking box 1 as well as box 2. On the other hand, if the demon hasn't put has put $0 in box 2 and you two box, then at least you'll receive $1,000. Whereas if you'd one boxed, then you'd have received $0. So the demon, in other words, the demon's already, before you make the decision, either put $1 million or put 0 in box 2. What you do or not doesn't causally affect what the demon's done, and So it seems you might as well take both boxes because irrespective of whether the demon's placed $1,000,000 or $0 in box two, you'll get $1,000 extra if you two box rather than one box. So this is sort of invoking dominance reasoning. So table 4 sets out the decision problem. If you one box, the state of the world is such that there's $1,000,000 in box one, then you get $1,000,000. But if you two box, you've got $1,000,000 plus $1,000. On the other hand, if there's 0 in box two and you one box, you get 0. But whereas if you two box, you get $1,000. So it seems that two boxing just dominates one boxing. Okay, so the dominance principle entails that one should two box, and basically we'll see that causal decision theory endorses two boxing, whereas evidential decision theory endorses one boxing. And the question is which one's correct. Right, okay, so the first thing to note is that this is a case where the state of the world is very far from being probabilistically independent of the agent's action. And so this makes it like both the exam case and the smoking case. So in both of those scenarios, there was no probabilistic independence between the agent's decision and the state of the world, and therefore the outcome. So, in particular, the probability that there's $1,000,000 in box two, conditional upon one boxing, is very high. So it's only 1 in a billion that there's not $1,000,000 in box two, given that you one box. So the probability that there is $1,000,000 in box two, given that you one box, is 1 minus 1 in a million. So it's very high. On the other hand, the probability that there's $1,000,000 in box two, given that you two box, sorry, I should have said 1 in a billion. The probability that there's $1,000,000 in box two, given that you two box, is 1 in a billion. And so basically, as a consequence of this, one boxing is just going to straightforwardly maximize evidentially expected utility. So basically, according to the evidential expected utility theorist, we take the utility associated with one boxing if there's $1,000,000 in box two, which is the one you select if you one box, multiplied by the probability that there's $1,000,000 in box two, conditional upon your one boxing, which is this very high number, 0.999, etc. And we add it to the utility that you get if you one box and there's 0. There's nothing in. There's $0 in box two, multiplied by the probability that there's $0 in box two, conditional upon your one boxing, which is a very low number. And the upshot is that the overall expected utility associated with one boxing is just a shade under $1,000,000. Whereas the evidentially expected utility theory, the evidentially expected utility of two boxing, what we do is we take the utility of two boxing if there's $1 million in the second box, and multiply that by the probability that there's $1 million in the second box if you two box, which is very low, or conditional upon your two boxing, which is very low, and we add that to the utility that you get if you two box and there's not $1 million in the second box, multiplied by the probability of there being not $1 million in the second box, conditional upon your two boxing, which is very high. And the upshot is that we get an expected utility of very close to $1,000. So the expected utility, the evidentially expected utility of one boxing is very close to $1 million. Of two boxing is very close to $1,000, just reflecting the fact that the probability that the demon has put $1 million in box two, conditional upon your one boxing is very high, and conditional upon your two boxing is very low. So evidential decision theory recommends one boxing. But what's interesting here is that although there's this correlation between one boxing and $1 million being placed by the demon in box two, this correlation isn't one due to causation of the demon's action by your action. Specifically, the demon acts earlier than you do, so your decision about whether to one box or two box doesn't have a causal influence on what the demon has earlier done. So it doesn't have a causal influence on the state of the world of whether there's $1 million in box two. And consequently, so the case is analogous to the smoking case, where similarly your decision whether or not to smoke doesn't have a causal influence upon whether you have the gene and therefore whether you get cancer. And it's disanalogous to the exam case, where whether or not you take the free bet does causally influence the state of the world. In other words, whether or not you get a first, and so causally influences the utility that you get. So because the agent's action doesn't causally influence the state of the world, and because the agent knows this, we know that the probability that the agent assigns to getting to there being $1 million in box two, if she were to one box, is equal to the probability that she assigns to the big $1 million in box two if she were to two box. And because of this, two boxing maximizes causally expected utility. So we know that her probability for the two counterfactuals is equal. So we can let X stand for the value, whatever it may be, that she assigns to each of the two counterfactuals, namely the counterfactual if she one boxes, then there'll be $1 million in box two, and if she were to two box, there'd be $1 million in box two. And then we can run the causally expected utility calculation. So the causally expected utility of one boxing is $1 million, which is the value of one boxing if there's $1 million in box two, multiplied by the probability that if she were to one box, then there would be $1 million in box two, which is X, added to the utility that she gets if there's not $1 million in box two and she one boxes, multiplied by the probability that if she were to one box, there wouldn't be $1 million in box 2, which is 1 minus the probability that if she were to one box, there would be $1 million in box 2. And basic algebra shows that the causally expected utility, therefore, of one boxing is 1 million times x. We do a similar expected utility calculation for two boxing. So the probability, or the utility that she gets if she two boxes and there's $1 million in the first box is 1 million plus 1,000. We multiply this by the probability that if she were to two box, there would be $1 million in box 2, which is x. And then we add to this the utility that she gets if she two boxes and there's not $1 million in box 2, which is just 1,000, which is the amount of money in box 1, multiplied by the probability that if she were to two box, there wouldn't be $1 million in box 2, which is 1 minus the probability that if she were to two box, then there would be $1 million in box 2, which is x. And again, basic algebra gives the upshot that the causally expected utility of two boxing is 1 million x plus 1,000, which is greater than 1 million x. Right? 1 million x plus 1,000 is greater than 1 million x. So the causal expectation of two boxing is 1,000 units of utility higher than the causal expectation of one boxing. So causal decision theory recommends two boxing. So, I mean, it's interesting. So it seems that philosophers actually are very divided about whether one boxing or two boxing is the rational strategy, and their division of whether one boxing or two boxing is the rational strategy tends to be reflected in whether they think that evidential decision theory or causal decision theory is the better version of expected utility theory. Those who like two boxing tend to be causal decision theorists. Those who like one boxing tend to be evidential decision theorists. So it's and there's no real settled view now on which is the better strategy. But I mean, I suppose it's worth thinking when you're thinking about reflecting upon your own views, not simply your intuition about this one case, the Newcomb problem, but also your intuition about related cases like the smoking case, which has a very similar structure to the Newcomb problem. It's just a bit less extreme in terms of its probabilities. So perhaps reflecting upon that case might help you think about what you think is rationally justified in the Newcomb problem case. Okay, so that's finally it. It's been a very long lecture. Hopefully you've taken breaks and giving yourself time to have a cup of tea and take a break from this fairly dense material. I'm sorry that it's a bit unideal. It's not nearly as nice as having a face-to-face seminar. I hope you've got something out of it nevertheless, and I hope you have also got something out of the reading. Please email me with any questions you have, and I will respond as soon as I can. Okay, thanks for listening.